All right, let's get our capacitance on. We're going to look at our RC circuits and in connection with timing to charge and discharge capacitor. We'll start without a resistor and then we'll add a resistor in. The first part will focus on concepts as well as graphs. The second part will add in some equations, and then if time we'll do a quick little example and practice more in class. So let's take a look at the schematic we see before us. We have a voltage source and a capacitor in series with a switch, and the switch is initially open, so the charge on the capacitor is 0. We're going to close the switch and we're going to look at the voltmeter as a function of time. We did this in class, so we're just summarizing the key here. So we know that initially, because there's no charge on there, there's going to be no voltage across the capacitor. And then when we close the switch, we know there's going to be charge building up on the capacitor. And if this is the positive side of the EMF, we know that this side of the capacitor is going to be positive and the negative side will become negative. So if you look closely, as the positives and negatives build up on the capacitor, they're in opposition to the EMF. So more charges means more voltage, but they just can't go on indefinitely. Eventually, the amount of charges on that the voltage will be high enough to be completely opposed to that one so that there's no more current flow. So it's going to go as high as the EMF. And it takes a very short amount of time. So if at time 0, we're at 0, at some point we're going to be at a maximum. I'll arbitrarily put it there. That's the EMF. And then how does it go up with time? It's not linear. We saw from class, or we can infer from class, that it's going to be something like that. And because that's an asymptote, that's definitely not a square root, that's an exponential. And we're going to see exponential is a common theme throughout this. And so after that, I shouldn't stop there, it will remain essentially at the EMF. Okay, it's just in opposition to our voltage, so that the overall potential across the circuit is now 0. And if the overall potential across the circuit is now 0, then the current is going to be 0, and that's going to be important for what we're going to look at in a second. Okay, so now if we look at current and charge as a function of time, we can deduce what has to happen. So before the switch is closed, we know the current is 0. There's a closed loop there. And then the instant we close the switch, what do you expect about the charge flow? Not the amount of charge on the capacitor, that's different. But the charge flow, is it going to be really high or is it going to be sluggish? Well, since there's no opposing EMF or potential from the capacitor, then we're going to have maximum potential across the capacitor. So we're going to have maximum current flow. So we'll begin at a maximum, which we'll call, let's just say I0 up here. And then as the charge builds up, we already said that the charges are in opposition to the EMF, so the voltage across the capacitor, while it increases, it's going to decrease the overall potential across the circuit, and therefore the current will decrease. And because there's no resistor in there, it'll decrease rapidly. So if I start here, and I know I'm going to end up at 0, then it drops like this. That's asymptotic. It goes to 0 but never reaches it. It looks like an inverse. It's not an inverse because it intersects here, the y-axis. That's another exponential. If we ask what's charge do with time, okay, I know at the beginning there's no charge on the capacitor. At some point, there's going to be a maximum amount of charge, and it's going to grow, but slow down its growth, and it's going to reach an asymptote. So it's symmetric to our I curve. All right, so you want to understand all three of those graphs conceptually. You won't have to do anything mathematically with them. Okay, and they should make sense. If you have any questions on that, anything's not clear, make sure you ask about that. Okay, so important generalizations that we just learned from this. Oh, I'm sorry, before I get to that. If we add a resistor, everything is the same. Okay, the only thing that's going to be different is the time over which this happens increases significantly. And you saw that in the lab when you added 1 or 2 light bulbs in series with the capacitor. So key generalizations. When initially connected to a voltage source, an uncharged capacitor, okay, will act like a short circuit. Or I'm just going to call it a short. And that's kind of odd because there is no connecting path here. That's an insulator. There's a gap there. But we have to look at it like this. As soon as we close this switch, the charges are going to come from here and there are going to very rapidly build up there because there's nothing opposing them. So you're going to have a maximum amount of current, like there was essentially zero resistance, and that's what we call a short. And the delta V across it initially is going to be 0, as we learned, when there's no charge on it. Then as we add more and more charge on here, we note that the voltage across the capacitor increases, but in opposition to EMF, and eventually the current will stop. So if the current will stop, then that's in essence we've got an open switch. Even though we didn't open the switch, it's still closed, we're going to get no more flow of charge. So in another sense, we can think of that charged capacitor when it is in series with a resistor and a battery has an infinite resistance. And the delta V across it, we already said is going to be the EMF, but I'm going to put a negative there to make sure we're clear that it's in opposition to the actual battery, let's say, or voltage source. The net voltage cross circuit is now 0. Hence, there is no current. Okay, let's look at discharging. Discharging is not going to be that much different. I just want to show you a schematic to show you how we might set up the simplest schematic where we could charge and discharge a capacitor simply by moving switches. So right now, as it's shown, it's in position Y. Let's pretend we started in position X. We had an uncharged capacitor. So we can see we have a complete circuit, and what's going to happen is this capacitor is going to charge up to positive and negative until its EMF, until the voltage across it is equal to the EMF. Then, the reason we charge this is so we can discharge it through a resistor. Okay, so then we can move that to Y, and we can discharge it and make the bulb light up again for a short period of time. And we want to understand how does the brightness of the current through that resistor change with time, the voltage across it, etc. So we expect that the current, when we initially go to position Y, is going to go from a maximum, or let's say I0, to 0. Okay, and the same is going to happen to the charge on a capacitor. It's going to start at a maximum value when we first close it, and then it's going to slowly decrease with time. And the easiest way to understand why this is more charge leaves here, there's just less push on the charges, so the current's going to drop. What's going to happen to the potential difference across the capacitor and also the resistor? Well, it's going to go from a maximum value, right, which was the EMF, and it's eventually going to drop to 0 as well. When there's no more charge on the plates, there's going to be no potential across it. So in all three cases, I, Q, and V, we're going to start at some initial value, and we're going to eventually end up at essentially 0, and it's going to drop exponentially. Okay, and again, never quite getting to 0, but close enough that it essentially is that. All right, again, if you have any questions as to where that came from, ask. Now what we want to be able to do is model that. How would we model the equation for that? So I'm going to do a very quick derivation. It's actually a lot of hand waving because it's a little bit beyond your math ability, but it's still nice to see. The best way to approach this is to apply Kirchoff's rule for looking at the voltage drop across here and the voltage drop across there and understanding that they have to essentially add up to 0. Okay, that's to conserve energy. So whatever positive drop I might have across the resistor is equivalent to a negative drop across the capacitor. So the most simple way to put that is that the voltage drop across the capacitor plus the voltage drop across the resistor has to add up to 0 at all times. Okay, so how do we calculate the voltage drop across the capacitor? Well, we can use the definition of capacitance and say that's nothing more than Q over C. Whereas the voltage drop across the resistor is Ohm's law is I times R. Okay, so what I want to do is I want to express some change as a function of time. So for simplicity's sake, I'm going to focus on charge. Okay, so I need to get the current out of there and substitute in something about charge. Well, I can use the definition of current as the rate of change of charge, right? The flow rate of charge. So I do that substitution, and I've got Q over C plus delta Q. That delta is important because it's instantaneous times some resistance. Okay, now I'm going to do a little bit of algebra. We're going to put all the Q's on the same side. So that becomes delta Q over Q is going to equal -1 over R times C times delta T. So at that point, what I want to do is I want to solve for Q. So delta Q over Q is like a time or derivative of Q. Okay, it's an instantaneous quantity over some infinitesimal time. This is starting to sound like calculus. That's what I want you to recognize here. So to get Q as a function of any time, I have to do the opposite of a derivative. I have to do an antiderivative or an integral. You haven't learned that yet. You don't have to know it here. But long story short, we end up is Q at any given time is equal to what we started with, Q naught. And we already know it's going to drop exponentially, so I need an exponential in there. That's E. And if it goes down, I need it to some negative exponent based on time. And then I need another factor in there to account for the actual physical situation. In other words, how much time it's going to take depends on, well, what resistance I put in there and what the capacitance is. It turns out that combination is nothing more than R times C. So there is my equation for how something loses charge as a function of time through a capacitor. If we want to look at current as a function of time, well, we know that current and Q are directly proportional to one another by definition. So this becomes I equals I naught e to the negative t all over RC. And then if I want to look at voltage, well, I and V are proportional by Ohm's law. So this would be V equals V naught dot dot dot. These are in your reference tables, so I'm not going to write them here. We saw this with our lab, okay? And now it's just an issue of how to apply it. Okay, so let's just look at a few aspects of this. Let me write the Q equation again. Q equals Q naught e to the negative t all over RC. Okay, this is where many of you are going to struggle, and I've seen in the past. So give yourself time to really examine what this equation is telling you. Let's say that at time 0, how much charge do we have? Well, conceptually, no, we're at maximum amount of charge. So let's see how that's borne out with the mathematically. So if t is 0 right there, this whole exponent is 0. E to the 0 is not 0, but it's 1. So our Q is equal to Q naught, just as we expect. So at time 0, we should have 100% of the original charge right there. So I'm looking at when we discharge. The first column is when we're charging. I'll worry about that later. Now, let's say, for argument's sake, our R is equal to 10 ohms, and our capacitance is equal to 1 farad. Let's just say that's the setup we have. Then the product of RC is 10 farad ohms. Well, 10 farad ohms, I'll let you work out, is the same as 10 seconds. So if our circuit is R times C is 10, then what that's saying is after 10 seconds, then I'll have my Q equals Q naught e to the negative 1. Okay? And e to the negative 1 turns out to be 0.37. Long story short, if my time is equivalent to 1 times the resistance and capacitance of that circuit, then I'll have 37% of my charge left. And then if I wait for another amount of time that's equal to 2 RCs, in this particular case 20 seconds, then what we'll find is that we've dropped not an equal amount, but a less amount, and we'll be down 14%. And then if I go to 30 seconds, which is 3 RC, we are down to 5%, then 2%, and then if we go to 5 time constants, 5 times R times C, we are less than 1%, which is essentially 0. Okay, so a really important thing about this is the amount of time that it takes to fully charge a capacitor or discharge it is dependent on the product of resistance and capacitance. And that product, R times C, is called the time constant, tau. And we're going to be talking about that. So after one iteration, and one iteration means 1 times RC, that amount of time, the charge of the capacitor already worked out is 37% of the full value, and then it falls off as we see there. So if you want to have an idea how much time does it take to fully discharge a capacitor, well, based on this chart, we see it's roughly 5 RC. So if our resistance is 10 ohms, and we got to connect it to a 1 farad capacitor, we're talking about 50 seconds. If I put 2 resistors in series, let's say the same resistors, this becomes 20, then RC is 20, so 5 times that, or 100 seconds, is when it's going to be more or less fully discharged. All right, I'm going to stop there. We'll do some practice in class. Come in with questions. I know that we're throwing a lot at you, and it's been a while, if not for the first time, working with exponential equations.